Hello and welcome. I'm Alan Taylor, Principal Researcher at the Materials Processing Institute. Today I'm delivering the paper Industry 4.0 Digitisation of the Normanton Steel Plant at the Materials Processing Institute. Agenda we'll be following today was an introduction to the Materials Processing Institute and the project itself, followed by a description of our steel making facilities, the selection of the Internet of Things platform, areas for improvement, the upgrades we made to networks, sensors and equipment, through to application of augmented reality and the future work. This is an aerial photograph of the Institute, based at Eston, Middlesbrough, established in 1944, firstly as BISRA, and then British Steel, Chorus, Tata Steel, and then in December 2014 became Materials Processing Institute. The Institute is independent, not-for-profit ROT. We have 4 research groups: advanced materials, low energy carbon, the circular economy, and digital technologies, of which I'm a member. We had a vision to create an open access Industry 4.0 demonstrator for the steel and process industries, utilising our steel plant. For this, we used Innovate UK funding under the project INTIFY, which stands for Industry 4 Technologies into Foundation Industries. We had several partners in this. There was Liberty Speciality Steel UK, Liberty Pipes, Hartlepool, Shifttech Limited, and TSC Simulations. This paper concentrates on the work that we actually undertook under this project at the Materials Processing Institute. The project started on 1st of April 2020, right at the start of the lockdown. So a lot of this work was done remotely, a lot of the brainstorming and meetings. So it's a very difficult start to the project. The UK already has demonstrators for Industry 4.0 at catapult centres. However, these were purpose-built from the ground up with Industry 4.0 in mind. Therefore, they avoid the issues of legacy equipment, the age, multiple data formats which we face by all process industries, not just steel, as they attempt to apply Industry 4.0. Our challenge, therefore, was to apply the 4.0 technologies to the Institute's Normanton steel plant. By doing so, we'd encounter all the problems associated with the aged kit and multiple data formats, together with the challenges involved with harsh environments that experience in the steel and foundation industries. Having done this, this would allow a smoother transfer of these technologies to other steel and foundation industry partners and clients. Our Normanton steel plant has a 7-ton electric arc furnace, combined vacuum degassing and ladle furnace, a continuous caster for casting billets and mini slabs, and depending on the section size, these could be any length from 15 meters to 36 meters. It's suitable as a direct mill feed. We also have ingot casting slabs 5 ton and 5.9 tons square. The first thing we had to address was selection of an Internet of Things platform. Initially, we considered creating one ourselves using platforms such as Microsoft Azure. However, we did a survey and reviewed of all existing Internet of Things platforms. And from this, we decided to evaluate the Siemens MindSphere and PTC Thingworks. We had quite a list of functionalities that were required from such a platform, and here's just a few on the list. We measured the functionality of the platforms against these. So, for example, ability to store data from several edge devices, process in real time, ease of connection to multiple data sources via OPC UA, ease of adding code to the platform, creation of mimics as well for the processors, ability to explore and export historical data. And one of the key things we were quite interested in was the ability to perform data analytics on the platform, together with the creation of machine learning and artificial intelligence models. Of course, cost and consumer support was also a key issue. At the end of the trials, we scored everything up and we chose PTC Thingworks version 9 as one that most suited to our requirements. Further, it has very good connectivity to Kepware version 6. We use Kepware on our pilot plant. This is a platform that allows connectivity to many different protocols for different sensors, instrumentation, PLC networks, and it's quite common use within the process industries. We use Postgres SQL open source database with the Thingworks for storing the data, and both of these were placed into a secured firewall demilitarized zone. I've got a diagram coming up next which shows you how this was done. This allowed external workers and project partners to securely view live melt and cast data, together with looking at live video streaming of the processes. It also provided the ability to connect to external customer databases and kept web services data transfer and modeling. So this is a simplified network diagram. On the left-hand side, we can actually see we've got the DMZ, which is demilitarized zone. Within this network, we have Thingworks itself, the Internet of Things platform, and its database. It's protected by a firewall, and via this firewall, we can actually connect to the Kepler server, which has the data from the Normanton steel plant. So it can get the data, take it through the firewall, and store it into the database. Also, as we go up onto the diagram, we go through the firewall to a router to the internet, and moving to the middle part, you can have the home worker. So the home worker is able to connect securely using SSL certificates and encryption to consume data from casts and the steel making plant. Moving on the diagram to the next part above, in a similar situation, we can have a client who has Kepler version 6, where we can get data from their plant via the internet securely onto Thingworks, where we can actually create mimics and do modeling. So it provides a very secure and reliable environment for collection and viewing and consuming of data. Another starting point for us, which again, because of the pandemic, was done remotely, was brainstorming sessions performed over Teams. And these were to identify the gap analysis in terms of our Industry 4 digitisation. The process mapping brainstorming was jointly undertaken with process operators and research personnel, where we identify the areas for improvement. A lot of areas for improvement were identified, and then we had to go through these and filter them for ones which are suitable for Industry 4.0 digitisation. Once we'd done that, we scored the areas for improvement based on benefits and ease of implementation. What we found was, because the steel plant is used for several different purposes, it resulted in different benefit scores between research and other process users. We chose low-hanging fruit, so we chose high benefits and ease of implementation to progress. And we also, at the same time, identified key performance indicators so we could benchmark our progress. These mainly being sort of slab service quality, fail starts, and availability. I'm sure you can read these. One of the key things and requirements for Industry 4.0 digitisation is the reliable and secure transmission of sensor instrumentation signals. So one of the first things we did was to upgrade our PLC network. It was using an older communication system, the control net, so upgraded it to Ethernet together with dual port cards to create a redundant ring. By doing this, we had a more secure and fault tolerant system, and with it being Ethernet, we had better system integration. We also installed a wireless network into the steel plant to allow communication with wireless sensors and tablets for process and maintenance engineers, and I'll show you some of this work a little bit later. The idea behind the tablets will be to allow process engineers to have access to process information, measurements, advice, and also provide maintenance engineers with access to maintenance records and equipment manuals. As part of the areas of improvement and gap analysis, we identified the need for sensors that we would require, in addition to the ones that we already had. So we purchased a variety of sensors. You can see here there's temperature ones, thermocouples, strand parameters, thermal cameras, usual measurements, pressure, flow, energy, weight, and steel analysis. So we progressed with the connection of existing sensors and instrumentation to our PLC network, Kepler and Thingworks. However, there's some legacy equipment and also things such as strand parameters aren't actually on the PLC network. And for these, we needed to create edge applications to allow connectivity. We're still in the process of undertaking a lot of this work. So we haven't got all the data in yet, but the sensors will allow the development of machine learning and AI models, which we'll use for predictive maintenance, operator advice, and product quality. We also investigated the use of Arduinos for connection to wireless mode thin film thermocouples. We developed various mimics and data displays, and here's an example of some of them. On the top left here, we have a caster mimic where we've got the caster, and we've got all the data relative to the cast being displayed. These mimics were developed using JavaScript, or mashups as described in the Thingworks platform. We also had data displays. So here we have a data display of the EAF line currents. On the bottom left, we've got the power and steam data display for the EAF. On the bottom right, we've got live caster mold temperatures. The setup that I've described allows remote viewing of mimics and data displays while watching live CCTV. As part of the project, we also installed the CCTV to the pilot plant. So here we have, it's actually Chris Oswin sat in his office. He's got two displays here. On the left, he's got the data display looking at a mimic of the caster while looking at the data. This is all happening remotely, and at the same time is observing the CCTV of a cast. A lot of the idea behind this is to allow our partners, research partners and clients, the ability to actually observe a cast remotely, both the data and the video streaming. Partners in the project, TSC Simulation, they did a laser scan of the pilot plant, which will be incorporated into a digital twin. And this is a short video showing the laser scan. And what you'll see here, it isn't actually a video, this is actually a laser scan you're looking at. And it's navigable, and you can actually move around it using the Xbox 360 controller. So it's a very short video, and it shows just moving through the plant. As I say, as a reminder, this is a laser scan, it's not actually a video. And then in the future, we'll be able to add other information to this, such as the label the processors and also process information, so the instrumentation, sensors, and measurements. Also with this, we can have photosphere pictures within it. So you can actually see moving again using the same sort of laser scan. We go to a photosphere, which allows us to look at a 360 view of the plant itself via a photograph. And the little diagram on the top left there just shows all where the photospheres are within this actual navigable model. We've investigated the use of augmented reality. So here we're looking at the continuous caster. On the right here, we have a researcher, and it's got his smart glasses on. And this is the view he's looking at. This data actually being shown here is simulated data, which was passed through the smart glasses. And it will show the mold level overflowing towards the end just to show the alarms. However, more recently, we've actually connected up to live data. So on the plant, we've been able to use the smart glasses and view live data as the cast is actually happening. With this, obviously, be able to provide operators with the required information to make informed decisions on the spot. But the use of augmented reality we're actually looking for is for remote assistance. And for this, we're using Euphoria Chalk. On the diagram to the left here, this could be from a phone, a video from a phone. So if we have somebody remote, for example, in Australia, and they need our advice on a piece of kit we've installed or help walk through, they could use their smartphone to video it. The expert back at the institute can then annotate onto the diagram here where he's showing the valve being rotated to open it. And the good thing about this is if you move the camera away from the object you're looking at and return it to, the annotations remain anchored to the initial object. What we're hoping from this is that we'll be able to provide remote assistance to customers and clients without the need for us to travel, thereby saving money for both ourselves and our customers. Another use of augmented reality is for expert capture. We live in an industry where a lot of our experts are not so young anymore, maybe retiring soon. So before they leave, we want to capture their expertise. And again, we're using the Euphoria expert capture for this. And what we can do with this, we can use the HoloLens to capture their knowledge. So for example, the diagrams here are actually our water modeling lab. So the expert would put the HoloLens glasses on, he'd move around the lab, setting it up how we'd normally do in practice. So starting the process off, so opening the valves, etc. The video then would be sort of annotated. So the one to the left here is you could have a trainee, he'd put the HoloLens on, and then you'd see these arrows pointing. So then he'd walk over following the arrows to the valves and we're presented with this view. So you'll see this view in front of him through the HoloLens, and superimposed on that is instructions and also a video. And this is from the expert actually opening up the valve. So he's saying here, open the air valve and check that the pressure is over 4 bar. There's a video demonstrating how to do it. This is the view he has through the HoloLens, and he can actually repeat it. Then you'll tell him to move on to the next with a set of arrows. So it's a lot more better than actually having to follow written instructions in to do this. So it's a good way of capturing experts' knowledge. So this is another thing we're experimenting with and looking at. Another form of augmented reality that we are investigating is the use of Euphoria Studio. So here we have parts of our caster. See the caster on the right there, and the straightener on the left hand side here. And what we've done here, we've used the LiDAR functionality of an iPad Pro to actually scan in the surroundings. And then from that, you can actually put information onto it. The idea being an operator can go back, hold up a tablet or his phone, and this bit of information will be anchored on it. So here it's sort of saying straighten the hydraulics, and it can give a pressure measurement. Or here we're looking at the strand, so an operator walking around can point his phone or a tablet at the strand and he'll get the temperature. That way he's getting the information as and when he needs it in order to make an informed decision. The data in this is currently simulated. It was just a proof of purpose concept that we're doing with the scanning and anchoring of the gauges and the tags. So that's a brief walkthrough of the work we're doing. It's still work in progress. The Intify project was initially intended to last for 2 years, but was put on stop a year into it due to the difficulties that Liberty Steel are experiencing. However, what we intend to do is continue the development of the Thingworks platform, the signals, creating more and improved dashboard, adding more equipment to it, creating more edge applications to connect legacy equipment. From the data we collect, we intend to do big data analytics, machine learning models, predictive maintenance, operator advice, and product quality. And we'll continue to develop the digital twin, where we intend to incorporate bespoke caster models into it, together with PLC models and live signals. We'll continue to develop our augmented reality, provide real-time data and warnings to process engineers. Thank you very much for listening.